are still on the methods in solving first order differential equation. So the second method that we will be introducing for today will be the exact differential equations. So at the end of this presentation, so the student should be able to identify whether a given differential equation is exact or not. And once the student was able to identify the exactness or determine the exactness of the first order differential equation, so the student should be able to find the general or the particular solution of the given differential equations. And again, so to differentiate the exact differential equation from the other methods for first order differential equation, so let's define what is an exact differential equation. So if a given first order differential equation is on this form, wherein there would be an m function of x and y, so multiplied it with dx, plus an n function of x and y, so multiply it with dy, and that is equal to 0. If such equation is said to be exact, if the partial derivative of the function m of x and y with respect to y is equal to the partial derivative of the n function of x and y with respect to x. So among the different methods in finding the solution of a first order differential equation, so it is only the exact and the non-exact differential equation, so which has a mathematical process that would determine whether a given equation is exact or not, because other methods could only be determined by merely looking at the differential equation or through trial and error approach. But for exact and non-exact, so there is a mathematical process. So that is the partial derivative of the given function either with respect to y or with respect to x. So similar with separable equation, so the application of exact differential equations would be on growth and decay as well. So as long as you were able to classify or identify a differential equation to be resolved using an exact equation, so therefore we can use the exact differential equation method in solving such applications. So example of which would be for the Newton's law of cooling and warming, so which is usually used in forensic, like for example that a victim of murder or the body of the victim was found out at a certain time of the day, and since the body temperature changes over a period of time, if we want to determine when was the exact time the suicide probably or murder occurred, so we can resolve that one so using differential equation. And if such equation would be classified as an exact differential equation, so therefore we could employ the methods in solving the crime. So through the determination on the time the body was found out, or the time the murder or suicide was committed. Okay, so to continue, there are actually two methods in solving or finding the general solution and particular solution of an exact differential equation. So one method is the method of exact differential equation, so which is usually the longer method. And while the other one is using the method of grouping, so which is usually the shortcut method. But let's try to enumerate first the different steps on or the different process in order to solve a differential equation using the methods for or methods of exact differential equation. So always the first method would be the test for exactness. So the test for exactness is as long as we are going to find the partial derivative of one function, so with respect to y, and then the other function with respect to x, and then it yielded to be equal. So therefore that is classified as as an exact differential equation. So if such is the case, then we can right away proceed with the integration process or the process of the exact differential equation. In this case, the second step would be we're going to integrate. Okay, so we are going to choose whether we're going to integrate mxy dx or the n or the function n of x and y dy. So usually for me, the one that I am choosing would always be the one that is less complicated to integrate. If m of x and y has a shorter number of terms, or it would be easier to integrate the m, then do it. If it is easier to integrate the n x y dy, then choose that one, so that the process would be shorter. But either case, so whether we're going to choose m or we're going to choose n, the function of m or the function of n, so it will arrive to the same exact answer. So if we had chosen to integrate the function of m of x and y, we're just going to add a function gy. But if we decided to if we decided to integrate the function of n of x and y dy, and then we are going to append a function of h of x. And then once we integrated the given function, so the next one is we're going to employ the partial derivative of the integral of the chosen function. And this time, so we're going to integrate it into, or we're going to partially derive it to the other variable. And then if we had chosen n of x of y, then we're going to partially derive it with respect to x. So the next step would be, so once you were able to derive the given equation, so we are going to find what would be the value of g of y, or what would be the value of the h of x. Take note that once, or to find the general solution, so we're going to equate and integrate using the given formula here. So we're in, usually we can detect whether we are arriving to the correct solution is that if we added g of y, so therefore once we equate it with an n function, it should arrive into a function of y alone. While if we will be arriving at an h of x function, so therefore everything on the right side should be x. So in such cases, so we'll be able to find the given value or the function. And once we were able to find the g of y or the h of x, so we can append it on our original function of x and y, and therefore, so that would be the integral or the general solution of the differential equation. So this is a bit tedious because there are a lot of process, but we need to be familiarized with the process. It's always on this way. We have to test for exactness. So once it is exact, we're going to integrate, and then we're going to partially differentiate, and then we're going to integrate it again. So to find the general solution of the differential equation. The next method, so which I think for me is the easier one, would be it has the same steps. So the first step would always still be testing the exactness of the differential equation. So we can only use methods of grouping as long as the differential equation is exact. Otherwise, we could not proceed with this method. But in the methods of grouping, so it is simpler as compared to the methods of exact differential equation because we just need to partially integrate the given differential equation. So by considering the variable of the differential or the differential to be the variable, and then the other one would just be considered as a constant. And then once we were able to do that, so we can group exactly the same terms into one. So we will arrive to multiple terms. However, there are terms so which are actually exact. So when I say exact, the variables and the constants are the same, the sign are the same as well. If it is positive, both are positive, so therefore those could be grouped. If both are negative, therefore those could be grouped. But even if, for example, one variable or the variables together with the constant are the same, however, one is positive, the other is negative, so those are not the same. So those cannot be grouped. So in such cases, those are actually canceled it out. Okay, so those are for the methods of grouping. So usually, as long as you were able to classify that it is an exact equation, the methods of grouping would be the easier one. But we can clarify this once we proceeded with our examples. So let's start right away. So with our first example. So for our first example, so we have 2xy dx plus x squared plus 3y squared dy, and that would be equal to 0. And to determine, okay, the first method is to determine the exactness of the differential equation. So we're going to let m, so to be equal to the function, so that it is multiplied with dx, and that would be 2xy. And then our n, so would be equal to x squared, so plus 3y squared. And from here, so we're going to partially differentiate m, so with respect to y. So that means we are considering y to be variable, while 2x are considered to be constant. So in that case, so it would just be simply, what's the derivative of y? So which is 1. So 2x times 1 would be 2x. So the partial derivative of m with respect to y is equivalent to 2x. On the other hand, so the partial derivative of n this time, I'm going to derive it with respect to x. So the derivative of x squared would be 2x, and 3y squared, so everything is constant, so y is considered constant here, so therefore the derivative of this would be equal to 0. So therefore, the given equation is actually an exact equation. So since this is exact, So let's proceed. So with our first step. Okay, so our first step would be to integrate. As I have mentioned, we have two choices. It's either we're going to integrate m or we're going to integrate n. As I've mentioned before, the simpler function so would be the one to integrate. So in this case, I'll choose m. So my f of xy, so which is the general solution of the f of x and y, so would be equal to the integral of 2xy dx. And since this is dx, so I'll be adding the function gy. And from here, so I am now going to integrate. So since the differential is dx, so I am going to integrate this one with respect to x. So and 2y is considered to be constant. So therefore the integral of x dx is x squared all over 2. So that's giving us x squared multiplied it with y. And then plus g of y. So that is our second step, so which is to integrate. So now that we have this one, so we are going to proceed with the next step, and that is the partial differentiation. Since we integrated it with respect to x, so this time, so we're going to partially derive the given function. So with respect to, so since this is g of y, so this is the one that we are deriving, so we are going to partially differentiate it with respect to y. So the derivative of x squared y, so with respect to y, so derivative of y is 1, and holding x squared to be constant, so that would just be equal to x squared. And the derivative of gy would be g prime of y. Okay, so now that we have the partial derivative of f of xy with respect to y, so since what we've used is m, so we're going to equate this one with n. So giving us the equation to be x squared, so plus g prime of y, and then n is equal to x squared plus 3y squared. And from here, so we can say, or we can cancel out x squared, and this is x squared as well. So giving us the g prime of y to be equal to 3y squared. And again, so integrating both sides, so giving us gy. So I'm just going to append dy there. So giving us y cubed all over 3 multiplied with 3, or that would just be simply y cubed. And rewriting our original function of x and y, and that is equal to x squared y plus gy, or in short, our f of xy so would be equal to x squared y plus gy, which is y cubed, and giving us the general solution of the differential equation to be x squared y plus y cubed, and that is equal to c. So giving us the general solution of the given differential equation. So the process is a bit tedious. However, we still have a simpler example. So let's have another example. So for the second example, so we have 4x minus 1 dx, so plus 6y plus 3 dy, and that is equal to 0. So in this case, our m is equal to 4x minus 1, and then n would be equal to 6y plus 3. And testing the exactness of the differential equation, so we're going to derive m with respect to y. So you can see here there's no y on 4x minus 1, so therefore everything is considered to be constant and its partial derivative is equivalent to 0. So similarly, the n could be derived with respect to x, and again the given 6y plus 3 is purely y and a constant, and there is no variable x, so therefore this is equivalent to 0, since the partial derivative of n with respect to y is equals to the partial derivative of n with respect to x, so therefore the given differential equation is said to be exact. So this time, so let's proceed with our next step, and that is to integrate. But again, we will be choosing which one are we going to integrate. Are we going to integrate m or are we going to integrate n? In this case, it doesn't matter. So which one are we going to use? Because both functions has the same number of terms, and it's not actually complicated to integrate either of the two. But to differentiate it from our first example, so instead of integrating m, so this time I'm going to choose n to make it different. So in this case, so I'm going to integrate 6y plus 3, multiply it with dy. So since this is dy, so I'm going to add, this time instead of g of y, so I'm going to add h of x. And then we are going to integrate. So the integral of 6y dy would be y squared all over 2, but 6 divides 2 would be 3. Okay, so giving us 3y squared. And then plus the integral of 3 dy would be 3y. And then plus, of course, the h of x. So next step would be the partial differentiation. So since this is h of x, so we are going to derive the function f of xy, so with respect to our variable x. So again, this is 3y squared. So everything is constant. So 3y is constant as well. So therefore, the derivative of this is 0. Derivative of this is 0. And h of x would be h prime of x. And from there, so we are going to equate the f of xy with respect to x. So since we've used n, so we are going to equate it to the other one, so which is the m. And then, so we will be substituting the partial derivative of f of xy with respect to x, and that is equal to h prime of x, and then m is equivalent to 4x minus 1. And then we need to determine what is h of x. And to do that, so we will be integrating both sides. In this case, so that would be dx. So the integral of h prime of x so would be h of x. Then the integral of 4x would be x squared all over 2, but 4 divides 2 would be 2, so giving us 2x squared, and then minus x. So therefore h of x is equals to 2x squared minus x. But from our original f of xy, that is equal to 3y squared plus 3y plus h of x. So from there, so the f of xy would be equal to 3y squared plus 3y plus 2x squared minus x. And finally, our general solution then, so would be 3y squared plus 3y plus 2x squared minus x is equals to c. So giving us our final general solution. Okay, so as simple as that. So next we'll proceed with another example, but this time so it's a bit longer, okay, but we will be arriving again to the same methods of solution. So the first step again is to identify. Okay, so I'll just be using m here, so to be equal to e raised to 2y minus y cosine of x and y. And then I will be deriving this one, so with respect to y. And that is, the exponential function is e raised to 2y, and then the derivative of 2y would be 2 dy, or I'll just attach 2 there. And then minus, so you can see here, so there is a product of y and the cosine xy. So in that case, so we will be using the product formula. So our u is y and v would be cosine xy. So the product rule, so we have u dv, so u would be y, and then the derivative of cosine xy so would be negative, right? So negative sine of xy. However, the derivative of xy so would be x. So I'll be attaching x there. So this would be u dv. And then I'll be adding plus v du. So our v would be cosine xy. And then the derivative of y is equivalent to 1. So giving us the partial derivative of m with respect to y to be equal to 2e raised to 2y. So plus, I'll be writing x first. So xy sine xy, and then plus cosine xy. So next, I'll have m to be equal to 2x e raised to 2y minus x cosine xy plus 2y. And deriving it this time with respect to x. So from here, so 2e raised to 2y is considered to be constant and x is the variable. The derivative of x is 1. So leaving us only to have 2e raised to 2y. And similarly before, x cosine xy, so it involves the variable x. So therefore, we will be using the product rule as well. And that is u would be x, and then the derivative of cosine xy would be negative sine xy, and the derivative of xy, considering x to be our variable, so that would be equal to y, and then that would be plus our cosine xy, and then the derivative of x, so would be equal to 1, and then plus this is a constant, so therefore that would be equal to 0. So giving us the final answer to be 2e raised to 2y, and then that would be plus xy sine xy, then plus cosine xy. And as you can see, the partial derivative of m with respect to y is equal to the partial derivative of n, so this should be n with respect to x is the same. So therefore, making the given differential equation to be exact. So our next step would be to find to integrate. So either we're going to choose an m or n. But again, so based from our given, so m has 2 terms while n has 3 terms. So in such case, so for me, I'll be choosing m instead. So that would be the integral of e raised to 2y minus y cosine of xy, and then with dx, and then I'm going to add g of y, and then we're going to find what's the value of f of xy. So by integrating our given, so with respect to x, so e raised to 2y, so would be considered constant, so we can move that out. So the integral of dx then, so would be x, so giving us x e raised to 2y. And next, so we have negative y cosine xy dx. So y here is constant, so therefore we could move that out. So I could right away write negative y, and then we are going to integrate cosine xy dx. So the integral of this, so the integral of cosine is sine, that would be sine sine xy. However, the derivative of xy would be y dx, and we have y, so we need to determine the neutralizing factor, and the neutralizing factor for our for the derivative of y dx, and that would be 1 over y, and then plus g of y. So simplifying the equation, so giving us f of xy to be equivalent to x e raised to 2y minus sine xy plus gy. And then, so we will be deriving the given equation, this time again with respect to y, because we have g of y there. So to do that, so this would be equivalent to, so x is constant, so y would be variable, So we'll have x e raised to 2y. So derivative of 2y would be 2 dy. So I'm just going to affix 2 there. So for the partial derivative. And then minus the derivative of sine. So would be cosine xy. And then, so since this is with respect to y, so the derivative of xy would be xy. So the derivative, so would be x. So x cosine xy. And then plus g prime of y. And equating, so the partial derivative of f of xy, so with respect to y, so we're going to equate this one to n. So giving us 2x e raised to 2y minus x cosine xy plus g prime of y would be equal to our original equation to be 2x e raised to 2y minus x cosine xy, then plus 2y. So which cancels out the 2x e raised to 2y and negative x cosine xy with negative x cosine xy on the right hand side of the equation. So leaving us the g prime of y to be equivalent to 2y. And integrating both sides, so giving us gy to be equivalent to y squared. And finally, rewriting our f of xy, so which is equal to x e raised to 2y minus sine xy plus g of y. So giving us to be the f of xy to be equal to x e raised to 2y minus sine xy plus gy is equivalent to y squared. So giving us the general solution, so to be x e raised to 2y minus sine xy plus y squared, and that is equal to 0. So giving us the final general solution of the given differential equation. So that is our third example, so which is a bit longer as compared to the first two, but still manageable. So let's proceed with another example. So the fourth example is similar with the first two examples. However, this time, so we will be using another method. Okay, so which is the method of grouping. Again, so similar with the first three examples, so we will be testing the exactness of the given differential equation. So the partial derivative of m with respect to y, so this is 0, and then that would be equal to 4. Now the other one is 4x minus 8y cubed. The partial derivative of n this time, so with respect to x, so that would be 4, 8y cubed would be 0. So therefore, it is exact. And since it is exact, so we can use the method of grouping, so which is more straightforward as compared to the method of exact equation. So to do that, So we're just going to take a look at the given differential. So if it is dx, so we're going to integrate it. So with respect to x, if it is dy, so we're going to integrate it with respect to y, and other would be considered as constant. So in this case, I'll have 5x dx. So I'm going to move out the constant, so 5, and then the integral of x dx, and then plus 4y dx. So 4y is constant, so I'm going to move that out. So that would be 4y dx. And plus, so this time, it shifted to dy. So to be our variable, so 4x would be considered as constant. So I'll move that out again. So 4x, that is multiplied with the integral of dy. And then minus, so 8 is the only constant here. And then we'll have y cubed dy, and that is equal to 0. And from here, we are going to integrate. So that will be 5. Integral of x dx would be x squared all over 2. Then plus 4y. Integral of dx is x. Plus 4x. Integral of dy is y. And minus 8. Integral of y cubed would be y to the 4th all over 4. And that is equal to c. So simplifying the differential equation, so that would give us 5 over 2x squared plus 4xy plus 4xy minus 2y to the 4th is equals to c. But take note, we're not done yet, because once we integrated the given equation, so we have to take a look at whether there are similar terms. So when I say similar terms, exact variable, exact constant, exact sign. So in this case, we have the 4xy. So 4xy is exactly the same as 4xy. So together with their sign. So this is positive as well. So if the two terms are exactly the same, so therefore, those two terms will be grouped as one. And that would give us the 5 over 2x squared plus 4xy minus 2y to the 4th is equal to c. So if I want to simplify this one, I could multiply everything by 2. So giving us 5x squared plus 8xy minus 4y to the 4th is equals to c. So yielding to our general solution. So to be 5x squared plus 8xy minus 4y to the 4th is equal to c. And as you can see, so this is a shorter method as compared to the method of exact equation. So direct to the point and easy to follow. So let's have the last example. So for our last example, so it involves again a triangle function. So sine y minus y sine x dx, so plus cosine x plus x cosine y minus y dy is equal to 0. So we're going to differentiate. So our m is sine y minus y sine x. So the partial derivative of m with respect to y, so would be cosine y, and then minus sine x. So on the other hand, so n is equivalent to cosine x. That's x cosine y minus y. So partial derivative of n with respect to x, so would be, the integral of cosine x is negative sine x. So plus cosine y, and that would be equal to 0. So making our given differential equation to be exact. And again, instead of doing the method of exact equation, we'll be solving these again using the method of grouping. And to do that, so I'll just have sine y. So since our variable or differential is dx, so I'll just have sine y, the integral of dx, then minus y, the integral of sine x dx, then plus, so this time it's dy, so cosine x is constant, then dy plus x, the integral of cosine y dy, minus the integral of y dy, and that is equal to 0. So the integral of dx would be x sine y, and then minus the integral of sine x would be negative cosine x. So negative and negative, so that would give us plus y cosine x, plus integral of dy would be y cosine x, and then the integral of cosine y would be sine y. So plus x sine y minus y squared all over 2 is equal to c. And again, so xy or x sine y and x sine y are the same, so therefore those could be grouped. So similarly, y cosine x and y cosine x are the same, so therefore we can group them as well. So giving us the equation to be x sine y plus y cosine x minus y squared all over 2 is equal to c. And multiplying the whole equation by 2, so giving us the general solution to be 2x sine y plus 2y cosine x minus y squared is equal to c. And that is our general solution. So using the simpler method of grouping. And that would be all. So for the exact equation, okay, or method of exact equation as the solution for first order differential equation.